Hello, my name is Ci-Jyun Liang from Stony Brook University. Today, I will present our research on an adaptive fractal Quadtree approach for efficient drone-based construction site safety inspection. This work is a collaboration with colleagues from the National Institute for Occupational Safety and Health in the US. Drones are increasingly used in construction for monitoring and safety inspections. However, traditional flight path planning methods like uniform scanning are inefficient and do not scale well with multiple drones. Our goal is to develop a more adaptive and efficient method for drone path planning using a fractal Quadtree approach. To optimize drone deployment, we first analyze the camera's field of view and its relationship with resolution and ground sampling distance, GSD. This helps determine the visible range and image resolution at various altitudes, which is critical for planning efficient coverage. Then we also evaluated three flight path strategies: random walk approach, zigzag approach, and also our proposed fractal Quadtree approach, FQA. So random walk is simple but inefficient. It's randomly select the traveling direction across the construction site. And zigzag is structured. It determines the coverage path in a more uniform way and is also predictable, but it lacks adaptability. In summary, traditional drone flight paths often use fixed resolution scanning, which leads to inefficiencies. Either they are oversampling simple areas or undersampling complex ones. Our proposed method, FQA, addresses this issue by dynamically adjusting the grid resolution based on the visual complexity of the construction site. The process begins with a coarse image of the site, which is analyzed using fractal image compression techniques. So here shows some result. As you can see, the more complex area, the drone will have more scan. And we apply a partitioned iterated function system, PIFS, which recursively divides the image into smaller blocks, which is called quadtrees, only where necessary. This is based on a predefined error threshold and complexity of the image content. And each block is evaluated using affine transformations to determine if it can be represented efficiently. This results in an adaptive grid. So larger blocks for a simple area and fine-grained blocks for complex zones. With a different size of the grid, we can have a different reflect their different complexities. So here is examples of the fractal compression. On the left-hand side is an original image, and on the right-hand side is a partitioned mapping by the different size of the grid. And you can see the overlap between each of them. And you can see from the image, the more complex area, we will get more fine-grained blocks, where the more simple area, we will have a more coarse grid to represent those areas. And here is the procedure. It is a recursive iterated process. We will have an original image and divide into the into domain blocks, and then we will continue the process to get the final result. Then once we get this procedure, we get the result image, we get the result grids blocks. drones are assigned to each blocks based on the required resolution. So for example, the higher altitudes for the drone at a higher altitude, we can assign the drone for a larger, simpler blocks. And for the lower altitude drones, they can do a more detailed scanning. They will focusing on the smaller size of blocks which are more complex. This not only reduces the numbers of images needed, but also optimize flight time and energy consumption for the drone. So in order to evaluate our system, we use two performance matrices to evaluate all the methods to evaluate FQA. The first one is compression ratio to make sure to evaluate the compression of the image, and also peak signal to noise ratio (PSNR). And for the evaluation, we use drone images from the real construction sites. The image covering the area over 64 by 64 meters. And here's examples. Here is one of example of the drone videos we used to evaluate. So here's a result. In our simulation, FQA reduced the number of required image acquisitions by up to 35% compared to uniform zigzag scanning. At the same time, while maintaining the image fidelities above 25 dB of the PSNR, you can see. So to ensure accepted image fidelities, the PSNR value should typically remain above 25 dB. So which our result achieve this requirement. So here are some other more results from the random walk and zigzag Random walk required over 13,000 steps for full coverage with two drones, as you can see here. And the zigzag, they can significantly reduce the required steps, but it still need 2,000 steps in the same situation with two drones. With four drones, they can achieve within 1,000 around 1,000 steps, but still it is much higher than using our proposed FQA result. So here is the path planning result of drones with FQA. So we overlap the result here. Drone path planning, we use two drones. One will cover at a higher altitude in the green line. The green dot, they will cover the larger size of the block, which is more coursed at higher altitude, where the other drone at the lower altitude will cover those smaller grid area with more detailed scan with different complexities. So in conclusion, our adaptive FQA method improves drone-based inspection by reducing redundant scans and optimizing flight paths. It enables scalable, efficient, and high-resolution monitoring of construction sites. This approach supports better safety inspection and resource utilization. So thank you for your attention. Please feel free to reach out to me through email and check out our website if you have any questions. Thank you.